My background is in infectious disease, but what I found was that the best way to study infectious disease was to try to figure out why people get them. And that inevitably leads to genetics and what it is that is inborn that leads to susceptibility. I think one of the most striking problems over the last few decades has been recognizing the interaction between immune deficiency and malignancy. And I think you have to differentiate that it comes in two major forms. One is the malignant potential of the mutated cells themselves. So GATA2 deficiency is an important example of this, where the cells that carry the mutation are precisely those cells that are at a risk for developing malignancy. Therefore, in those diseases, complete elimination of those cells is going to be important. In contrast to those diseases in which the malignant potential exists in the cells themselves, it is those diseases in which probably it is the environment in which those cells occur. And it is probably a cytokine or an immune milieu that allows the development of malignancy. And here I'm thinking about diseases like Job syndrome or PI3 kinase deficiency, where it may not be required to have complete replacement of all hematopoietic elements in order to eliminate the malignant potential. And I think the dissection of these syndromes and the understanding of the mechanisms of malignancy and how those relate to underlying immune deficiency have an enormous impact on how we understand the development of malignancy in normal humans. As we know now, marshaling the immune response through these checkpoint blockade inhibitors has been an extraordinary advance in the treatment of cancer, which puts cancer and its progress smack back into immune function where we all live. And trying to understand how each immunodeficiency is different and how each cancer is different, and therefore how each treatment will be different, is going to be a critical component of the next few decades. So I think that the bad news is that the next steps are hard work. It will be very careful dissection of each immunodeficiency and why does that immunodeficiency lead to that cancer. Just as an example, today Alain Fischer was talking about the role of keratinocyte expression of specific immune receptors in the development of severe HPV and then squamous cell malignancy in patients with, say, gamma C deficiency. This is an extraordinary example of just how complex each individual tumor is going to be. In contrast, for instance, in GATA2 deficiency, where HPV-related malignancies are very common and severe squamous cell disorders are very common, this is eradicated by bone marrow transplantation. In contrast, in the gamma C and the JAK3 deficiencies, those are not eradicated by bone marrow transplantation in the squamous cells, suggesting that exactly which cell expresses exactly which receptor will have a critical role in understanding exactly which cancer somebody is susceptible to. And so, just as no one drug or one antibiotic can prevent all complications or all infections, no one approach is going to handle all cancers or all susceptibility. And so it is dogged, hard work. That's the bad news. The good news is that we now know where to search, and we know that if we try to differentiate the cancers and the susceptibilities, there is a lot to be learned and a lot to be gained, and we now have drugs and treatments that are very successful for each of these areas. So why am I confident that there will be progress? Because there's always progress. When people work hard on topics that they're interested in, they come up with solutions. And the alliance between scientists and physicians and pharmaceutical developers right now is extremely strong. And ESID has been a nucleus for pushing this forward, for getting together scientists and doctors and developers into one forum